It's just a science project.
Silent breed is people!
You know, a doctor friend once said the same thing to me. Frankenstein was his name.
It's alive! It's alive! It's alive!
That sounds like something out of science fiction.
Please explain to me the scientific nature of the whammy.
We live in a spaceship, dear.
So? Yes, science!
Program complete. Enter when ready.
Hello and welcome to episode 214 of Science on Top. Today is Sunday, the 14th of February, 2016. I'm Ed Brown, and today I'm joined by Lucas Randall.
Hey, Ed.
And theoretical astrophysicist from Melbourne University, Dr. Katie Mack. Welcome back.
Thank you. It's good to be here.
It's great to have you on because there was a little bit of excitement among astrophysicists this week. The story goes back to 1915, really, when a German-born patent clerk published his theory of general relativity. And it was a theory that fundamentally changed our view of gravity. And over the next 99 years, all of the predictions that Einstein made were proven correct, all except for one, until an observation made in September last year and announced last week. Katie, can you tell us what gravitational waves are?
Sure. So Einstein's big insight in general relativity was the idea that gravity comes from distortions in space-time. So space-time is sort of like, you can think of it like the fabric of reality. It's kind of hard to explain, but it's this idea that the three dimensions of space are joined by one dimension of time, and they're all kind of malleable together. And so if you have a massive object in space somewhere, that kind of bends space-time in around it. And so that causes things like orbits can happen because if the space-time is bent, then anything moving through the space-time is curved with the space-time. And so orbits happen around planets and things like that because space is bent. Gravitational lensing happens where light can be bent around massive objects because it's going through space-time and it's trying to go straight, but space-time is bent. And so there's this idea that space-time is this sort of malleable thing that gets bent by masses. And one of the consequences that comes out of that idea is that the force of gravity that you feel has to travel from one place to another, and it travels by waves in this space-time fabric. And it travels at the speed of light. This is all part of Einstein's theory that when masses are moving around, accelerating in the universe, that motion creates ripples in space-time, and those ripples travel out at the speed of light, and they can distort space-time as they travel. So the way that a gravitational wave distorts space-time is that if you have a gravitational wave coming right at you, then it'll stretch you in one direction while squeezing you in the other, and then vice versa. So if you have a gravitational wave coming right at your face, then your body will get a little bit taller and thinner for a moment, and then it'll get a little bit wider and shorter for a moment, and it'll kind of oscillate back and forth that way as the wave passes through.
So that's what that was. I was wondering.
Yeah, they say.
That's funny. While you were describing that, Katie, I was picturing your hand movements from the video that did the rounds this week of you describing exactly the thing.
Yeah,
with your hand making sort of an oval.
I was in fact doing that, even though you couldn't see it because I'm used to. That's how I explain it. So, so this was Einstein's big idea, gravitational waves, and it was something that he wrote down in 1916. And when he wrote it down, there was really no hope of ever observing it because these were tiny, 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 tiny distortions. The gravity is a very weak force, and these stretches and squeezes are really, really weak. And anyway, it's hard to imagine how if you have a yardstick and it gets a little bit longer and then it gets a little bit shorter, it's, the thing you're measuring with is also getting a little bit longer and a little bit shorter. And so it's hard to imagine how to measure that. And it's only, since this was something that people thought maybe we can start testing, that people found really cool ways to try to measure those distortions. And that's what the LIGO instrument does, the Laser Interferometry Gravitational Wave Observatory. It's designed to measure those distortions in space-time as gravitational waves pass through.
So these are sort of, and you were talking about the direction of the gravitational wave, and this is a wave that would be going out in all directions, essentially, wouldn't it, from whatever was causing it?
Yeah, so it's not entirely uniform in all directions. If you have two for instance, two black holes orbiting each other, they produce gravitational radiation, and they actually produce it stronger sort of up and down than in the plane of the orbits. So if you're looking at a system face on where the two things are orbiting around each other, then you get the stronger gravitational wave production that way.
Right. And that's what we saw, what was measured in September, wasn't it? It was two black holes that merged, essentially, wasn't it?
Yeah. So the kinds of signals that LIGO is best optimized to see are things like the mergers of two black holes. So if you have a couple of black holes that are orbiting each other in a binary system and they merge together. So initially, these two black holes would be going around each other. If they're far enough apart, then it's a reasonably stable orbit, especially if there's no gas or anything nearby. It's hard to lose energy in that orbit. But because they're massive things moving around, they're radiating gravitational waves, and that takes away some of the energy of this orbit, and so it causes the orbit to decay. It causes the bodies to move closer and closer. And in those final moments when the two black holes are just about to merge into one black hole, that produces a big burst of gravitational radiation. And that's the kind of signal that LIGO is best set up to look for. In this case, it saw black holes that were around 30 times the mass of the sun. And it saw them merge together in this sort of burst of radiation. And it was able to see as well the effects of that sort of composite black hole that was created sort of wobbling into a spherical orientation and like radiating just a little bit of gravitational radiation at the end as well. And so it was able to measure the masses of both of the objects, the black holes that came together, as well as the mass of the final object, and found that the gravitational radiation carried away so much energy that it was as though you took three times the mass of the sun and turned it directly into energy in a fraction of a second. And that was the energy that was taken away with gravitational radiation.
One of the other things that really jumped out at me about this story, though, was a lot of the reporting was very casually referring to the collision, the merger of two black holes, as though this is just something we see all the time. But that in itself was pretty huge news.
Yeah, this is the first direct observation we've had of binary black holes coming together. You know, we've seen systems where there's something else orbiting a black hole. That's how we see black holes generally, is that something else is orbiting or falling in, and we see the radiation caused by that infall or that, accretion of matter. This is the first time we've really seen two black holes orbiting each other without, some kind of electromagnetic signal. So that's cool in and of itself. And these are also quite large black holes. I mean, we know how to make black holes of around, say, 10 solar masses, because stars that are that massive tend to form black holes when they die, and those are the kinds of sizes of black holes you expect. You don't really expect stellar collapse to create black holes of 30 solar masses. That's kind of large. And so it suggests either that stars were quite massive to begin with when they created black holes, or that these black holes have been growing somehow, or that there have been other mergers earlier on that got them that big. But that's one of the things that physicists and astronomers are excited and curious about, is how you get two black holes of about 30 solar masses together.
Yeah, I mean, that seems incredibly unlikely outcome, that you'd end up with two, such large, massive stars together in that situation in the first place, to then end up with two incredibly rare, massive black holes that then go ahead and clack together like this. It seems like one of those things that scientists really hate, is all of these exceptions to rules and things that are a bit rare. It seems both messy and exciting.
Well, you have to understand there's a bit of selection effect, right? Because if they were a little bit less massive, they would have had a smaller signature, a smaller gravitational wave output. And if they were quite a bit more massive, they would have been in a different frequency range that's harder for LIGO to see. So this range between about 10 solar masses or 1 solar mass up to maybe 50 or 100, I think is where LIGO is optimized. So these are the kinds of ranges of black hole masses that are easiest to see, and The larger end of that are brighter signals in the sense they're the higher amplitude gravitational waves.
So it could be that there are these binary black holes merging frequently throughout the universe.
Yeah.
And it's just that these particular one we were particularly tuned to receive.
Yeah, I mean, there are probably solar mass, 1 solar mass black holes or 10 solar mass black holes merging all the time, and they're not as strong a signal, so they'd be a little bit harder to see with LIGO unless they're nearby. We know that supermassive black holes merge as well. Those are quite hard to see with LIGO. They're in the wrong frequency range, but there are other experiments like pulsar timing arrays, which is where you sort of look for gravitational waves passing by timing pulsars all over the universe really carefully and seeing if the timing gets a little bit off. Those would be better for looking for supermassive black hole mergers. And if we ever get the space version of LIGO, called LISA or ELISA, now it's European LISA because NASA backed out. If that ever happens, that'll also be more tuned for these heavier black holes as well.
Okay, so can you tell us how LIGO works? This is an L-shaped sort of 4-kilometer laser something. Is that right?
Yeah, it's a really cool instrument, and it's one of the most precise experiments ever done. Really incredibly impressive. What it is there are actually 2 sites. There are 2 separate instruments, one in Washington State and one in Louisiana in the U.S. And both of them are a big L-shaped thing with 4-kilometer arms, and each arm is a vacuum tube. So it's a tube where all the air is taken out, and it's got lasers going down each arm and mirrors set up so that the lasers go down and they bounce back and forth, and then they come back to the center and they set up mirrors again so that the 2 laser beams interfere perfectly. So they're the same wavelength, the same intensity, and they're set up so they perfectly cancel. So the crest of one wave meets the trough of the other, and you should get 0 light if everything's fine. And then they have to put in all sorts of seismic isolation to keep the mirrors from moving. And what they look for is the light, a little dot of light to appear where that indicates that the cancellation is off. So this is taking advantage of a really, really cool and important trick. So I said before, it's very hard to measure the length of something changing because your measurement tools are also changing length. So how do you do that? The way you do that with this laser thing is you take advantage of the fact that that light travels at the speed of light in a vacuum, no matter what you do to it. So even if space-time is stretching, light travels at the same speed through it. And that means that if the length of one of these arms gets a little bit longer as a gravitational wave passes through, the light just takes a little longer to get to the end. And that means that as a gravitational wave passes through, one arm gets a little longer, the other one gets a little shorter, and that causes that perfect alignment of these light beams to be a little bit off, and so that cancellation doesn't work anymore, and you get a little bright spot on the detector. And that's the signal that LIGO looks for is this distortion of the alignment through one of the arms getting a little bit longer and the light taking a little bit longer to get from one end to the other.
Okay, so one arm gets a little bit longer. What are we sort of talking about a measurement here, like a millimeter or a centimeter or something?
Oh,
how precise is this?
Way harder to do than that. It's so the arms are 4 kilometers long. The distances we're looking at, the change of distance, is something like 1/1000th the diameter of a proton. So just
of a proton.
Yes, staggeringly tiny measurements. It's about
1/1000th the diameter of an atom, but the actual nucleus inside.
Yeah. So it's a factor of 10 to the minus 21 or 10 to the minus 22 of the distance. So that turns out, if you do the math on that, that's 4 kilometers goes down to about 1,000th of the diameter of a proton. So it's really, really tiny. I mean, the same. So a gravitational wave passing through between us and Alpha Centauri, the nearest star to us, 4 light years away, would produce a change in distance of a few millimeters. That's the kind of scale we're looking at.
Right, because this collision with the black holes was 1.3 billion light years away. Is that right?
Yeah, it was 1.3 billion light years away, and it's also just that these are very small shifts. The gravitational waves are very weak. They do this very little bit of motion. But you imagine, 1.3 billion light years away. Just think of the immense amount of energy it takes to shift distances that far away from the object. So it's really so much energy was put out, but it's still, it's a weak force, and it does just a small shift. So the achievement to be able to measure that kind of shift over 4 kilometers with these lasers is just incredible.
Blown away.
Yeah.
I'm blown away that we can do that.
Yeah, I am too. And a lot of people in the physics community just looked at this and thought this is never going to work. It took a lot of build up to get there. The instrument that detected these things. Both of these 2 sites in America detected the same signal, offset by some tiny amount of time that corresponds with the light travel time between the 2 objects. But anyway. Right. These 2 instruments are called advanced LIGO. The initial LIGO, so the first run of the experiment, went for several years, and initial LIGO didn't see anything because it wasn't sensitive enough. So it's taken a really long time.
It could only do a tenth of the width of a proton. That was useless.
Yeah, something like that. It was just below the sensitivity where they expected to see a reasonable number of events. With advanced LIGO, if they hadn't seen anything, after a while, we would have gotten really suspicious that something had gone wrong, either with the theory or with the instrument. So advanced LIGO, everybody said, it has to see something if this theory is correct. Initial LIGO, it was one of those things where if they could have gotten lucky, there could have been a really big merger event nearby during the time it was on that would have given enough of a kick to these mirrors. And it turned out that initial LIGO just wasn't lucky and wasn't sensitive enough to see stuff that would be more common.
So we ramped it up. We cranked it up to 11, and that's the result. I'm just still staggered by the 1/1000th of a proton figure. There must be so much shielding and everything, because an earthquake, a ball dropping nearby, anything is going to affect something that precise.
A truck going down the highway half a mile away is enough to throw it all off. There are a lot of sources of noise. They have incredibly careful seismic isolation. They created special fibers that hold up these mirrors that are designed just to be the most isolating thing that you can imagine. And then there's also the fact that you have these 2 different sites. So if a truck drives by in Louisiana, the site in Washington is not going to hear that, and so you can cancel out some of these local sources of noise through that. A big enough earthquake or thunderstorm could affect both sites, but in general, you can cancel out a little bit from having 2 sites, and that's part of why they do that.
And is this something that it heralds a new kind of astronomy, doesn't it? Before this, we've been reliant on electromagnetic radiation, light, radio waves, whatever. This is measuring space-time itself, really.
Yes, and it's and people have said that it's a new window on the universe, and that's entirely true. Previously we've been able to look with electromagnetic radiation of different frequencies, and every time we get a new sort of electromagnetic band, we see something new. So when we went from just visible light to radio, we started to be able to see the universe in an entirely different way because we could see the radio side of the universe. So with visible light, you can see the stars really well. You can see stars in other galaxies. With radio, you could suddenly see the gas between the stars. You could see these large sort of glowing lobes of radio emission, all those kinds of things. And we got a much better insight into how the universe was put together, how galaxies worked when we figured out radio. Then we've been studying the universe in neutrinos for a few years. That's been very interesting. We've seen a lot of interesting stuff with neutrinos, cosmic rays, but now we're able to look at space-time itself. And that's like getting a whole new channel and whole new sense of the universe. And that's letting us see things that we would never have been able to see with other sources. I mean, these two black holes that came together, they might not have been accreting gas. They might not have been putting out any kind of electromagnetic signal. They might not have produced neutrinos, anything like that. It's just, I mean, black holes are space-time objects. You know, they have no real form. They have a size, they have a charge, sometimes they have a spin. That's it. They don't have any other properties. And unless something is falling into them, there's kind of it's very hard to observe them directly. But now that we have gravitational observatory, we can see these distortions in space-time themselves and see how they're changing, and we can study the buildup of matter in the universe. You know, as black holes come together to grow, we can start to see how you get from stellar mass black holes, the product of stellar collapse, to the supermassive black holes that we see at the centers of galaxies. Because so far, it's been very hard to see anything intermediate because they don't accrete very much matter, and they're not in these sort of binary systems with stars where you can see something going around them. So we know they have to be out there, these intermediate mass black holes, but we haven't been able to observe them. And these kinds of gravitational observatories are going to give us access to that.
And I was hearing a radio program today where they were saying that you can increase the definition, I guess, of this by having multiple LIGO sites. So another one in the southern hemisphere would be good. I don't know, maybe in Australia it's been known to happen that we do scientific experiments here. Yeah,
there's been some work in Australia. There's some stuff going on in Europe and in Italy, and also I think there's a site proposed in India. And basically, if you have a third site, you can triangulate the signal and you can figure out exactly where it's coming from. At the moment, with these two sites, we have sort of a vague impression of where in the sky it comes from. We know that this source was somewhere in the southern sky, roughly, but we don't have a very precise location for it.
Is there any? Are there any other types of observations that came along with this one? Was there a GRB detected at the same time, or anything else that sort of helps us get an idea of just where in the sky it was?
There have been searches. So I was just looking today at a paper put out by the LIGO collaboration where they were looking for neutrino signals at the same time, and there were a couple of candidate neutrino sources, but it was unclear whether they really matched up with this source, this black hole merger. There was also a paper put out by a team not connected with LIGO, using data from the Fermi gamma ray satellite. They said that they found a really weird gamma ray burst at something like 0.04 seconds after the LIGO detection, which might be connected or might not. It's a very preliminary analysis, and that has to be investigated further. But it's possible, but it's kind of unclear for this kind of merger. It's a little unclear if there would be any electromagnetic or neutrino counterpart. But we're looking for that, and we might be able to see that. And there are other sources that we'll look for. LIGO should be able to see certain kinds of supernovae events potentially, and so there are other events or like gamma ray bursts that are two neutron stars coming together, coalescing, the so-called short gamma ray bursts. If LIGO can see those, then we would expect an electromagnetic counterpart, definitely. And so that's another situation where LIGO would use other observations and other sort of signals and hopefully see something interesting.
Yeah. Gotcha. Yeah. So just going back to something that you touched on earlier on in terms of giving us another tool to use to observe the universe. I did read something the other day saying that this also gives us a potential tool to look back beyond the cosmic microwave background, because we don't have this opaqueness to deal with when we're talking about gravity.
So that's so you were asking about if we can see beyond the cosmic microwave background. In principle, yeah, gravitational waves can do that, and that's the primordial gravitational waves that we thought were discovered but actually weren't a year or two ago. Those would be signals from before the cosmic microwave background, so within that first 300,000 years of the universe. LIGO can't see those frequencies. And there wouldn't be any really massive objects that would produce gravitational waves in that time, because it's before massive objects really came together. But with other instruments, with observations like looking at patterns in the polarization of the cosmic microwave background, we do hope to see signals of that. And there are even proposals for space-based laser interferometers that might be able to see some signatures from the cosmic microwave background, or from the early universe before the cosmic microwave background. So that's something that's still a little ways off, but hopefully we'll be able to do that. And it's using the same principle of this stretching and squeezing of space-time, but at a different sort of frequency than LIGO. When I'm talking about the frequency, in this case, I'm talking about how quickly the mirrors are moving, basically how fast the stretching and squeezing is happening.
Right. And you mentioned the BICEP-2 experiments from a year or two ago, which were since discredited, which was very disappointing for a lot of people, I think.
Yes.
We're fairly certain about the LIGO results.
Yeah.
This has been peer-reviewed and everything? Or? It's
been peer-reviewed. It's also just a much cleaner... There are ways in which it's a much more direct detection. So the BICEP-2, the problem with BICEP-2 is they were looking at patterns in the polarization of the cosmic microwave background, and dust also causes polarization in the cosmic microwave background, and they underestimated how much dust was in the way. With the LIGO, the things that make it really clear that it's a real detection. One is that the same signal was seen in both sites, both in Washington and Louisiana. It was a signal that matched just absolutely beautifully with the numerical relativity simulations. Everything just matched so well with theory, and there was a lot of testing. there were a lot of different sort of analysis pipelines and stuff, and it was just for the last several months since the detection.
Yeah, this was discovered in September, so obviously there's lots of analysis done.
So there's been tons of analysis, and it has been peer reviewed, and it's been very, very carefully checked. So I think there's almost no chance that this thing could go away.
Wow, terrific. Yeah. What actually happened then with that BICEP-2 experiment? Are they still working there, or is everyone just like, well, with that discredited, we hang our heads in shame? No,
they're still working on it. They're working on BICEP-3 now. It's a harder experiment now because we know that the dust foreground is a lot worse than we thought it was, and so it's going to be harder to dig that signal out just because there's so much dust in the way, and we know that now. But they're still working on it. They're working with the team that runs the Planck satellite, which is the cosmic microwave background satellite, and hopefully they'll see something interesting. But at the moment, all the data they have so far is within the noise from the dust. I mean, I should say also, you mentioned before that this experiment was discredited. I wouldn't call it that. It's just that the discovery was not a discovery in the end. So it was called a discovery when it shouldn't have been called a discovery because they had underestimated their foregrounds. But the experiment itself is still a good experiment, and the data is still good data. It's just that the foregrounds are really strong.
Right.
I did read on the conversation, Tara Murphy from University of Sydney, she detailed how the LIGO team would intentionally inject fake data into the alerts as a way of checking that the double checks on the data were working, and that they could identify erroneous data and remove it from the experiment. Do you have any other background on or more information on that, Katie?
Yeah, so there was they had a system of testing their analysis pipelines where they actually had something inside the experiment that could physically move the mirrors a little bit in the same way that a gravitational wave would do it. And they set this up for initial LIGO. And they did one of these tests where only a couple of people knew that this was being done. So there were a couple of people who were in charge of these fake injection events. And those people didn't tell anybody else when they were going to do it or what they were going to do. And so they did one of these fake events, and it was and the people who were monitoring the experiment saw this really strong signal. They called it Big Dog, the Big Dog signal, and they analyzed the signal, and they wrote up a paper, and they got it all ready, and then they opened the envelope, and it was not real, which must have been such a bummer. I mean, I can't imagine. So that would have been bad.
It's like the worst April Fool's prank ever.
Oh, I know. I mean, they knew that it could have happened. Like, they knew this was part of the experiment, but still, what a disappointment. But this time, they actually when the machine came online, it was actually so early in the process of setting up the experiment and getting starting the data taking that the people in charge of fake injections were not ready yet to do the injection. Like, they hadn't set up their injection process yet, and so they couldn't have been fake because they was so early. The machine had only been on for 2 days when this event came in.
Bob, was that you? Hey, no, I didn't touch it.
Yeah.
Was it you, George?
Yeah. So I was reading today about somebody talking about like what it would have taken to fake this signal, and it's like you would have had to have hacked into both data streams at both sites in some way that's basically impossible, or you would have had to like cut a hole in the vacuum tube in which the experiment runs and like move something, because when they opened up the experiment after the run was finished, there was no apparatus in there to do the fake injection. So like it would have been really, really hard to fake this thing.
Still, if it was Hollywood, it would have been like 6 keystrokes.
Right.
And that would have been it.
Yeah, I can see Tom Cruise abseiling into the detection vacuum.
Yeah. I mean, the article
moving it 1/1000th of a proton and getting back.
Yeah, the article I read called it a Mission Impossible, but actually impossible situation.
Yeah.
So it's a very good point you just brought up about the timeliness of this, because there is on sciencemag.org, there's a timeline of the history of the search for gravitational waves, and some really key things happen right at the last moment here. You've got this the initial runs of the first LIGO in 2002 to 2010, and then you've got this upgrade period, a $205 million upgrade of the LIGO detectors from 2010 to 2015. Then they turn it on in September 2015, and then they get that first hit. It's huge.
Yeah, it is kind of amazing that it happened so soon after they turned it on. But I mean, that part was just lucky. It's not entirely luck that they saw anything, because we knew from astrophysical models that they should expect to see something within the sensitivity of the experiment, in a reasonable amount of time. But that it did happen so very early in the run was sort of a stroke of luck.
And so, is there anything left of Einstein to test, to predict? Is everything that he said turns out to be right? Or
I think it's an interesting topic, like people talking about Einstein being proved right. This is the final prediction of his theory in terms of like a big new phenomenon that's been conclusively proven. He started with things like gravitational lensing, and then in 1916 he wrote this paper talking about gravitational waves. There's no other like big, we should see this thing in the universe prediction of his from general relativity. All that's really left to test is kind of the borders of the theory, like where, how far you can stretch these fundamental laws that general relativity writes down. So, the relationship between mass and gravitation and how signals travel within space-time, all of that, those are laws that, based on how Einstein wrote them down, should stretch from the smallest scales to the largest scales. But we know that there have to be alterations to that at the smallest scales, at least, because we know that general relativity and quantum mechanics don't work well together. And so either Einstein's general relativity doesn't apply at the tiniest scales, at the quantum mechanical scales, or, quantum mechanics has some kind of tweak that we don't understand yet. And theories like string theory are attempts to reconcile quantum mechanics and gravity in a way that would sort of alter, both of these ideas in some sense. So we're always going to be testing the edges of general relativity. We're also testing that on the largest scales. There are suggestions that what we perceive as, or what we call dark energy, the accelerated expansion of the universe, there are suggestions that that could be related to the law of gravity changing at the very largest scales in a way that Einstein didn't predict. So we're going to keep testing every part of Einstein's theory in order to see if we can find the limits of the validity of the theory, and that never stops. So science is really just a series of better approximations, and we never sort of assume that we have completely described the truth of reality. It's always a matter of we're getting a better model that fits the data a little better, and so we're going to keep doing that.
Excellent.
But in terms of things that little Easter eggs that Einstein left for us to find in the universe, this is the last one.
I did, just speaking of Einstein, I quite liked something that was there's a wrap up of scientists respond to this discovery on The Conversation, and Keith Riles from the University of Michigan wrote that fittingly Einstein himself indirectly helped make those lasers happen, of course talking about the lasers used in LIGO, first by explaining the photoelectric effect in terms of photons, for which he earned a Nobel Prize, and second by creating, along with Bose, the theoretical foundation of lasers which create coherent beams of photons, all with the same frequency and direction. It's kind of cool that he has this theory, and he goes, and here's what you need in order to be able to build the detector to test for my theory. I just love the synergy of that.
Yeah, I mean, in his time, he could never have imagined that we could ever build anything that could test gravitational waves. But it turned out that a lot of the things that he described for us in collaboration with other people, in some cases, were really, really helpful.
And you mentioned dark energy before, so I was just going to throw this out there. Does this gravitational wave, does this sort of new method of astronomy, does this do anything, or do we expect it to help us determine anything about dark matter or dark energy?
Well, the main thing that it'll help us determine how space-time works in the strong field regime, which is not related to dark energy, because dark energy is very much weak field in the sense that it's the largest scales and so the weakest gravity. But it'll tell us something about sort of the fundamental nature of space-time, which could be useful as we're thinking about things like dark matter and dark energy. And it'll tell us a lot about the buildup of matter in the universe, which is something that we have a lot of trouble getting accurate simulations for. And that might tell us something about dark matter. So when we're trying to make predictions for what to look for in terms of dark matter, like if dark matter is annihilating and creating high energy particles, and we're looking for those annihilation products, a lot of things that go into the modeling for that rely on understanding better how matter builds up in the universe, how galaxies form, because as black holes and galaxies are coming together, they bring their dark matter with them, and so the way that dark matter is sort of clustered in the universe depends on also how regular matter and black holes and things are clustered in the universe. So as we're able to get a better picture of the buildup of mass in the universe, the growth of structure, we will be able to use that to refine our models of what to look for with dark matter.
Wow. It's so exciting. I love this. But I've just got to ask, how does this affect you, Katie? Do you just stop? The announcement was on, I think, was it Friday or Thursday night, I think, our time. Do you just I'm not doing anything on Friday now. It's going to be media all the time. Do you just not do anything from then on?
Yeah, well, I mean, I knew that this was going to be such a big deal and such a sort of once in a lifetime event from the point of view of just being a really major discovery. I knew that I was probably not going to get any work done once things started kicking off. So, I let the university know that I'd be available for talking to the media on Friday, and I ended up talking to some people even Wednesday and Thursday as they were sort of preparing all their big stories, because it was pretty clear that this was what the announcement was going to be with all the rumors flying around. yeah, I mean, I stayed up for the press conference, which happened at 2:30 in the morning, between Thursday and Friday. Not only did I stay up for the press conference, I also I was with a group of astrophysicists at Monash to watch the press conference, and a couple of them were on the LIGO project. So after the press conference, they were finally able to talk about it, and so we were grilling them about the paper and trying to get more details and everything. And I ended up not getting home till 6:30 in the morning that night, and then I slept for 2 hours. I slept between 8 a.m. and 10 a.m. And then I ended up doing a live blog for The Guardian and being on TV for Sky News. And it was a lot of, there was a lot going on. There were a lot of people to talk to, and there's a lot of demand for commentary on the discovery.
Can I just you just reminded me of something that came up back in September. Lawrence Krauss made mention of a potentially huge discovery, and I think I may be remembering this wrong. We either had Helen Maynard Casely on the show, or it was in a Twitter exchange. I mentioned how, wouldn't you be really quite annoyed if this was your project and then someone else sort of took that, or took it upon themselves to announce it.
Yeah.
Now, Krauss wasn't involved with the project, was he?
No.
He must have got this from somewhere else, or maybe someone's inadvertently let something slip, because there was a huge amount of secrecy around this, despite his sort of early rumor spreading.
Yeah, no, but nobody who was on the project was allowed to talk about it, and that was partially caution, because if until the analysis,
they didn't want another bicep.
Yeah, they didn't want another bicep, and until the analysis was fully done, they didn't want to discredit themselves by announcing something that they'd have to retract. And also this was a massive, many decade kind of effort, and it's only fair that the people who put it all together and the people who put in all the hard work should get the glory, and be able to have a big announcement and sort of present it as this is this thing that is done, and we've had this discovery, and we're going to be here to talk about it. I think that's only fair. So a lot of people were annoyed that so many rumors were going around so early, and that people were sharing information they shouldn't have been sharing. But in the end, it was such a big event anyway. Even though we all pretty much knew what they were going to announce, it was still an incredible moment to watch the press conference and see someone say we have detected gravitational waves.
The official moment is still just as exciting and palpable, even with all the rumors.
Yeah.
And I'm actually glad that the rumors were about the week before or whatever, because that gave us a chance to reach out to you and say, do you want to jump on? Whereas I think if I'd asked you at 6:30 on Friday morning, you might have been a little less excited about it.
Well,
or coming on to talk to us,
I mean, I'm always happy to talk about stuff like this, but it definitely was definitely helpful for some people to know a little bit ahead of time, just to be able to have all the best information available right when the announcement came out.
Yeah. Did you have anything else to say, Lucas?
No. I'm still, my head's spinning in 1,000 different ways as I'm thinking through this. But no, it's.
I've just got
it's been awesome.
1/1000th of a proton going through my head. It's like, what the hell?
Oh, dude, it's just mind blowing. And Katie's explanation of how LIGO actually worked. I've seen diagrams and I've read a few things on it, but actually, it finally clicked tonight. Yeah. When Katie was explaining, it was like, oh my god, it's the cancelling out of the signals that's the key bit. I didn't get that before.
It's such a complicated experiment. I think a lot of times when people describe it, it's hard to get all this stuff in together. But I mean, the thing that I think is so cool about it is that they're using the constancy of the speed of light as a sort of trick. They're sort of tricking the light into telling them this thing that happened by the fact that it can't speed up to catch up to the mirror that's just been moved by space-time. I think that's really cool.
It is cool.
It's very cool. Dr. Katie Mack, thank you so much for coming on and blowing our minds today.
Thank you. It's a pleasure.
Where can people find you on the internet?
Well, the usual place I hang out is on Twitter. I'm on Twitter as @AstroKatie. I've also got a website, astrokatie.com, and I'm on Facebook at facebook.com/astrokatie. So those are the main places that I have stuff online. I haven't updated my website in a while, but I will at some point. So you can find me there.
Excellent. And as usual, we'll have links to that and some other stuff about gravitational waves on the web at scienceontop.com/214. And we really appreciate your thoughts and feedback. We don't get a lot of feedback, but if you want to share some, tell us what we're doing right, send us an email, feedback@scienceontop.com, or catch us on social media, Twitter, Facebook, all that. And thank you, Lucas, for joining us once again.
No worries, Ed. Thank you.
And thank you, everyone, for listening. We'll be back again next week, putting science on top of the agenda. Join us then.
In between drinking deer blood and defaming Steve Waugh, Shane Warne's stint on I'm a Celebrity, Get Me Out of Here has been just as eventful as everyone had hoped. The spin bowler kicked things up a notch though, educating his campmates with a compelling and watertight theory about the history of mankind.
If we've evolved from monkeys, why haven't those ones evolved?
Yeah.
Because I'm saying aliens. We started from aliens. Look at those pyramids, Bonnie. You couldn't do them. You couldn't pull a bit of rope, those big, huge bits of brick, and make it perfectly symmetrical, and couldn't do it. So
No.
who did it?
It has to be from another world.
Has to be. That's why I reckon we did too. Whatever planet they're on out there, they decided that Earth, they're going to start some more life on Earth and study us.
But scientifically, we have the same, so many similarities.
Similarities to monkeys.
Yeah, so I don't know.
Maybe they turn a few monkeys into humans. They turn into humans.